Welcome, everyone. For today's prep, we're going to start to look at derivative rules. So we've seen the limit definition of derivative, and we can do that, but it's kind of a lengthy process. There's a lot of work involved. Dealing with all the different cases of those 0 over 0 forms can be tricky. So it turns out that there's derivative rules that can kind of help simplify this process for us so that we don't always have to go back to that limit definition. So in this set of notes, we're going to start to look at our basic derivative rules. So things where we have constant multiples of functions or adding and subtracting functions. And we're going to start with kind of two basic functions. Both of these are linear functions. So linear function of the form f of x equal to mx plus b, and then a constant function, also a linear function. So f of x equal to b. So when we calculate the derivative, what the derivative is actually giving us is it's telling us the slope of our curve at any point. So if we have the function mx plus b, well, we know what the slope is of this function at any point. It's just the slope of the line, m. So when we differentiate a function mx plus b, what we're really doing is we're just figuring out the slope of the curve, and this function has constant slope. So the slope is just m. Now when we're dealing with a constant function, so f of x equal to b, well, same kind of deal. We know what the slope of a horizontal line is. It's always 0. So the derivative is 0 there. Okay, so we want to keep these in mind. When we have a term mx, the derivative of that is just m. And when we have a constant b and we're differentiating, we get 0. So when we differentiate this b here, it's not showing up. We just end up with a 0. So the only contribution is coming from this mx term. Okay, so those are kind of two ones that are helpful to get out of the way. So our first major rule that we're going to look at is the power rule. So this tells us how to differentiate power functions. So things of the form x raised to a power r. And we can remember the rule. You almost want to think of it, though, like a 3-step process, though. So the first step is to bring down the old exponent and put it in front. So we're going to take the exponent, bring it down, put it in front. So that's what we get there. So it's kind of like step 1. Step 2 is whatever variable we're using, we keep it the same. So we keep our variable the same. So we start with an x, we're going to keep an x. And then step 3 is we subtract 1 in the exponent. So it would be r minus 1. Okay, so that's our power rule. Let's see it in action. So let's look at example 1, and we'll keep this rule in mind. So our function is f of x equal to x squared, and I'm going to probably show more work for these first few that we do, just until we get the hang of this. So once you can do these, you're probably going to go right from the function right to the answer. But let's look at the first one here, f of x equal to x squared. And our derivative, we're going to call it f prime of x. And so the way this power rule works is we're going to take our exponent 2, we're going to bring it down, put it in front of the x. So we're going to have 2 there. Then we keep our variable the same. So our variable is x, so we just keep it x. And then we subtract 1 in the exponent. So our exponent was 2, and then we're going to subtract 1. All right, so that's it. And 2 minus 1 is just 1, and we don't normally write an exponent of 1. So like I said, once you get the hang of this, you're probably not going to show this step. You're probably going to go right from here, right to the answer. All right, let's try x cubed. So here the function is called f of x, so our derivative, we'll call it f prime of x. And we're going to do power rule again. So this is a power function. We're going to take the exponent 3, bring it down, put it in front. So we're going to have a 3 there in front. We have variable x, so we're going to keep the variable the same. And then we're going to subtract 1 from the exponent. So 3 minus 1 is 2. All right. So nice integer exponents there. Well, what about root functions? So we're going to look at kind of the next two, square root x and 1 over x. These we're going to see a couple strategies to help us with the differentiation process for these. So for root functions, we want to rewrite these as a power function. So in general, when we have the nth root of x, we want to rewrite that as x raised to the 1 over n. So we rewrite an nth root as a fractional exponent. And then once we have that, now this is a nice power function that's ready for kind of doing power rule with. So let's rewrite this square root. We're going to rewrite that as x raised to the 1/2 power. All right, so this format is nice. We're ready to differentiate. So we'll call our derivative f prime. Our exponent is 1/2, so we're going to bring that down, put it in front. We keep x the same, and then we're going to subtract 1 from this exponent. So again, you might be able to do this all in one step, but if you can't, especially with these fractional exponents, it doesn't hurt to just kind of show a little bit more work, at least until you get the hang of it. And so let's do this off to the side. How does this 1/2 minus 1, what do we get when we subtract that? So if you need to do this, it's okay. So 1/2 minus 1, get a common denominator, so 1/2 minus 2 over 2, and then 1 minus 2 over 2. And once we have a common denominator, we can subtract the numerator. So 1 minus 2, and that's just -1. So this would simplify to 1/2 x raised to the -1/2 power. So if you got to do this work off to the side, it's okay. All right, so that's for root functions. That's our strategy for root functions. Now, when we have fractions where the numerator is a constant and we have x in the denominator, so we can write this as 1 over x, another way to kind of look at that. When we have fractions like this, our strategy in this case is to rewrite using negative exponents. Again, the idea is we want to write it as a power function so that we can use power rule. So right now this is not a power function because it's actually a quotient. It's 1 divided by x. But our strategy is we're going to rewrite this as x, and there's a hidden exponent of 1 there. So we keep the exponent the same, but then we just make it negative. And that negative gets rid of the fraction for us. All right, so once we have this negative exponent, now it's a power function, so we can just use this power rule. So we bring down the -1, put it in front, keep x the same, and then we subtract 1 from that exponent. So we end up with -1 minus 1, or just -2. And that's perfectly good. You can leave it like this. Or if you did want to simplify it, you could simplify this or rewrite this back as a fraction. So not necessary, but you could write this as -1 over x squared. So get rid of the negative exponent and it goes back to a fraction. And then we can just take the -1, put that up top. Okay. So that's power rule. Now another rule we're going to look at is the constant multiple rule. So the way we use this is essentially what this says is if we have a constant k times a function of f of x, and we want to differentiate that whole thing, what we can do is we can focus in on differentiating the variable part, that function f of x, and then just multiply the result by the constant k. So we can focus on differentiating the variable part, And any constant multiple that was in the original thing that we're trying to differentiate just kind of stays where it was. Another way to think of this is what we're doing is we're bringing the constant out in front of the derivative. So if we're trying to differentiate a constant times a function, we can focus on getting the derivative of the variable part and then just multiply that result by the constant. All right, so let's see this rule in action. So we'll look at maybe one or two of these, and we'll save the rest for class. All right, so let's look at the first one here. We want to differentiate. So again, this d dx means calculate the derivative of all the stuff inside here with respect to x. All right, so if we look at what we have a constant 2 times a variable part. So what the constant multiple rule says is the 2 is just going to stay there in front, and then we can focus in on just getting the derivative of x to the power 5. And for that, we're just going to use our regular power rule. So let's just kind of zero in on that. We're going to take the 5, bring it down, put it in front of the x, keep our x the same, and then we're going to subtract 1 from the exponent. So we're going to go 5 minus 1, which is just 4. And we can simplify this so we can multiply those two constants together, and we get 10x to the 4. So again, once you get used to these rules, you're probably going to go right from here right to here. So you can think of it as we're bringing the 5 down and we're multiplying it with the constant that's already there in front. But what's really going on is the 2 just kind of sticks around, and then we're differentiating that x to the power 5. All right, maybe let's try one more. Let's look at this x cubed over 4. So we want to differentiate this. And right now, it's not written quite as nicely as we want it. So the idea here is we want to break any constant terms. We want to separate constant terms from variables. So we're going to rewrite this just slightly, and we're going to write this as 1 over 4 times x cubed. So we can always do this with fractions. 1 over the denominator times the numerator. And the benefit of viewing it like this is now we have a constant multiple times a variable part. So when we go to calculate the derivative, the constant multiple is just going to stick around in front. And then we can concentrate on getting the derivative of that variable term. So the 1 over 4 just kind of stays. And the x cubed, we're going to differentiate. So we bring down the 3, put it in front of the x, keep x the same, and then we're going to subtract 1 from the exponent. So 3 minus 1, 2. And usually a good idea when you have kind of multiple constants out in front here multiplying each other, actually do the multiplication. So we could write this as 3 over 4, and then our x squared. And you know, like I said, once you get the hang of this, you're probably not going to show these middle steps. Okay, so just one little comment here. Why does the constant multiple stick around when, if we go back to this constant function, when we have a constant, it differentiates to 0. So the difference is when we're differentiating a constant function, there's no variable here. So remember, a derivative is kind of measuring how much our function's changing. So when there's no variable, well, it's just a constant. It doesn't change. So the change is just 0. But in the case of these constant multiples, the constant multiple is attached to a variable. So it does kind of maintain its influence a bit in the derivative. So for constant multiples, it's just important to note, a constant multiple doesn't differentiate to 0. Kind of sticks around. All right, so let's look at one more rule, and we're going to do one example of this. So we have our what we call our sum rule, and this also works for subtraction as well. So the way to read this derivative rule is if we have two functions that we're adding together, f of x plus g of x, and we want to differentiate this whole thing, well, we can focus in on the first variable part, differentiate that, focus in then on the second variable part, differentiate that, and then the addition, or if it's subtraction, just kind of stays the same. And it's worth noting, does not work for multiplication and division. So it doesn't work for multiplication and division. Only works for addition and subtraction like this. So let's try an example. We're going to look at example 3. And let's just do the first one. So x cubed plus 5x. We want to differentiate this whole thing. Well, we look at the first term, we look at the second term, and we're just going to differentiate each of those on its own. So for that first term, we want to differentiate x cubed. So just that, derivative of x cubed is, well, we're going to get the derivative of that. We'll get the derivative of 5x, and then the plus sign is just going to stay the same. So the plus sign here is just going to stay the same. All right, so we do our power rule on that x cubed. Bring down the 3, keep x, and then subtract 1, so we get 3x squared. And then the derivative of 5x, well, this is that mx form. So this part is just a line. And we know the slope of a line is just that constant that's in front, so 5. If you forget that, though, you could always use power rule for this. So you could also think of this as x raised to the power 1. And then when we do power rule, we bring down the 1, keep x the same, and then subtract 1 in the exponent, and we just get x to the 0, which is just 1. So you could think of the derivative of 5x here. If you want to remember it as just the slope of a line, perfectly good. If you want to use power rule, the 5 just sticks around, and then the derivative of x is 1, so we just end up with 5. Okay, so we'll practice more of these in class, though. So we'll see you there. Bye-bye.